The first problem's topic was flow through porous media, and the goal was to find how long it would take to fill up the dog's bowl using this nice homemade filter. So the related equations are the Bernoulli equation, the extended one, Darcy's law, the volumetric flow rate, the height, volume of the cylinder, and the Reynolds number. The assumptions made here were laminar flow because the word trickles was included in the description, so that would cue into it moving slowly. And that allowed us to assume that Darcy's law applied, so you can use that, and that the velocities at point 1 and 2 are negligible, and delta P equals 0, so it's assuming that this water flows purely due to the difference in height and gravity. The cited properties used are the density and the viscosity, which are both found at table A-9 at 20 degrees Celsius. To find the solution here, the Bernoulli equation was simplified, so you get the friction is equal to the gravity times the differential height, and then from there you can find the superficial velocity and use that to find the volumetric flow rate. The time is then equal to the volume of the dog bowl, as seen in the equation above, pi r squared height, and then you got that to be 10.03 minutes, so a little bit of a wait, but not too bad. And then the Reynolds number was verified, and it was found to indeed be laminar. The next problem discussed internal fluid flow with friction loss and pump analysis, and you're trying to find the required pumping head to maintain flow rate and drawing the typical centrifugal pump curve. The equations used were the head form of Bernoulli, the velocity equation, the Reynolds number, and head loss in a pipe, and then the friction factor for both laminar and turbulent flow. The assumptions made were that alpha equals 1, and then the velocity at point 1 is much less than velocity at point 2, so it's negligible, and starting out at a height of Z2 equals 0, and P1 and P2 are both at atmospheric pressure. The cited properties are density, viscosity, and then both of these were from table A9 at 15 degrees Celsius, and then the KL, the loss coefficient, is 0.5 found in table 8.4. So the solution of this one, first you would simplify the energy equation to get the pump head, and then you found the velocity of the liquid, the Reynolds number, so then you know that the first part at least is turbulent, and then you calculate F prime. With that, you can find the head of pipe 1, and then you need to do the same thing for pipe 2, so find the velocity, then the Reynolds number. Found that the second part of the pipe is actually laminar. We did sigma over D, roughness, and then F prime again, but this time for laminar. So you can find the head of pipe 2 and then the total loss. You just sum those together, and then you find the total required pumping head. And then for B, this is just a typical pump curve. You see the pump performance curve, the systems curve, and operating point, and then SI units are feet in grams per minute. So this next problem covers external fluid flow. The related equations used here were the drag equation, and to find the weight force and the buoyancy force, the area, the volume, and the Reynolds number. The assumptions made was that the water flow over the sphere is laminar, and then the cited problems were from table A9 at 20 degrees Celsius for water. So the solution for this one is you find the forces on the ball, do a force balance, force drag equals weight minus the buoyancy force. Then you evaluate that, so then you're able to solve for V and substitute that into that equation, and then last but not least, verify that it is indeed laminar flow, so these equations apply. Question 1 addresses compressible flow and more specifically choked flow. The equations used were for the speed of sound, the Mach number, the stagnation temperature and pressure, and the critical pressure. The assumptions were one-dimensional isentropic compressible flow for an ideal gas, assuming this ideal gas is air, which leads us into the properties K equals 1.4, found from table A13, and the CP value found in table A1. The solution then is first solving for the C constant, and then using this number to find the velocity, because we're given the Mach number. And then from here you can find the stagnation temperature and pressure, and then you finally solve for the critical pressure. The physical meaning of this is if you were to lower the pressure anymore, the mass flow will not further increase. The topics in question 2 are microscopic mass and momentum balances, boundary conditions, and analytical and numerical solutions to Navier-Stokes. The related equations were the continuity equation in spherical coordinates and the z component of the incompressible Navier-Stokes equation, because that's the direction that there is velocity. The assumptions that were made were steady state, so the time derivatives will go to 0, irrotational, so the theta derivative will go to 0, Newtonian, laminar, incompressible, so the density can get pulled out and go to 0, fully developed, once again, it only goes in the z direction, not the radial direction or the theta direction, no slip at the walls. For the boundary conditions, symmetrical, also for the boundary conditions, and the differential pressure is equal to 0. The cited properties are from table A9, which is used in the numerical solution. To solve this, first the continuity equation was simplified, and this was using the assumptions, and then the Navier-Stokes equation was simplified. Then once you get that, you can use the two boundary conditions to solve for Vz analytically. The first boundary condition was symmetry, because it's a pipe that is symmetrical, so there is no flux in the center. No slip at the walls, because the walls of the pipe are not moving, so this lets us say that at the walls where little r equals big R, the velocity in the z direction is 0. And then when you're solving it numerically, you separate into the second derivative and the first derivative, where you can plug in the finite differencing equations, and then through those equations, you plug them into Excel, allow your iterations, also plug in your boundary conditions, so you can see at r equals 0, Vz of n equals 0, and then r equals 5, the outer radius of the pipe, Vz also equals 0. And then the Reynolds number was verified because this is supposed to be laminar, even though it is not laminar in the slightest. We still use these equations because that's all we know how to do.